We need a new asteroid class. So I sort of have the opposite view that if you look at where biology has been going the last 100 years, you start getting more and more complicated schemes for how to classify things. Where now not only do we have species, but we have subspecies, and we have varieties within subspecies. And it gets to the point where you start having, one member of each group, and you have a million groups, and it gets to be burdensome. And so I think that more useful than a class would be to simply devise a spectrum where you can say it's located here on this spectrum of all the detected asteroids.
Yeah, I would have to agree with you that my suggestion of a new class is mostly just aimed at saying that if we lump in Alma Theta with the F-types, that ignores information that the detailed spectrum presents us, that we don't see present in all of the, we don't see present in all. We may see present in some that I just haven't found yet. But the majority of F-types that I've looked at do not show that absorption feature and are not necessarily related to Alma Theta. There could be some process disguising their spectrum, completely obliterating any trace of that olivine or pyroxene. I don't think so, because Alma Theta is carbon-rich, the most carbon-rich of the meteorites. And the carbon is an opaque material that happens to decrease the absorption strength. And so if the others should, by that logic, which might be wrong, should have an even stronger absorption. So we should see that there. So yeah, I agree. This is a unique case right now. Doesn't deserve its own class.
Just a comment, we don't need really new class, we need really new observation and quality observation.
Exactly, yeah, and I think that we should maybe get away from just lumping them into broad classes and start looking at distinctive features and identifying the chemistries, looking at those.
I would like to ask a general question to you and to other researchers from your research, that about the numbers of solenoids and metalloids. Are they constant, or they increase in a definite time that as a result of oxidation of planet or other body?
Okay, I'm not sure I completely followed. It was the number of them constant in
Number
time?
of solenoids and metalloids that hit the Earth, are it constant or increase in a definite time?
I don't think anybody has noticed any definite change in the frequency, in how often they hit us in recent history. But there's another comment here.
I think geologists are here. I read some papers about research in Sweden, where in some quarries were found layers of fossil meteorites, which indicates that in some 500 million years ago, the flux of the GL type chondrites were few orders larger than it is today. And this event is associated with some breakup of asteroid family in the asteroid belt. So this is one of examples that the flux of the meteorites on the Earth is not constant in time.
Yeah, thank you for that. Very good point. Yeah, that's a great example of using the geological record of meteorite hits, which is a very rare thing for us to get. Instead of just over human history, which is very short compared to the age of the Earth. But yeah, the flux, the incoming meteorites and asteroid impacts almost certainly has not been constant over geological time.
Was a good question.
Was a good question.
Okay.
Okay, thank you again.
Yeah. Thank you for hanging in so long as is now. We have 2 more talks to give. The strategy of those 2 talks is going to be, I'm going to sort of completely swamp you with a ton of information in 20 minutes. And then by the end of that time you'll be all asleep and dozing and tired and really ready to go home. And then Lucy will come in and she will host you with a whole bunch of cold ice. And so that will wake you up again. And then after that, after her presentation, we'll John Maria and have a look at the meteorites and so on, and we'll make the end of the story. So this talk is my own talk. So I'm a little bit more nervous about it than giving you some talks. The topic is searching for the Euro-like parent body, and I think that Mark did an excellent job in introducing the various problems associated with trying to do that. But given that Asteroid 2008 TC3 got so much excitement and attention, I got a number of people to collaborate in this effort. And some people that are really sitting on the source of the data, including Richard Linzel and Francesco De Meo. And so with their help, we've come up with a number of new spectra of objects that are candidates. And we found a whole bunch of other 1998 KU2-like objects. And so this will promise to be an interesting talk. Just because of that. But there's another aspect that I think is really exciting, and that is this whole story about what a Euro-like parent body is. And I borrowed Jason Heron's slide without his permission. No, good. Because if you go and look for the Euro-like parent body, you have to be looking for a Euro-like parent body. Which is a really strange thing. So this work has now been submitted to Mathematics and Planetary Science. These are co-authors. Just to start off, very simple. We've seen this before. The asteroid belt. That's where our asteroid came from, somewhere in the asteroid belt. Sun, Mercury, Venus, Earth, Mars, and then here's Jupiter. Somewhere among these asteroids is where we suspect 2008 TC3 originated. Now the belt these days looks really messy. We see that, so that Paul showed us a picture. This is a nice composite by the Minor Planet Center. All these green dots are asteroids. So it's a huge number. The red ones are the ones that are coming close to the Earth, like Paul indicated. Now it's nice that there's so many because that helps us with the searching. This is Jason's sort of summary of what we think is a Euro-like parent body. Something that started out as a sea continent-like object, what we call a protoplanet. An object that had grown to a significant size. I have heard sizes ranging from 100 kilometers to 200 kilometers that people want this thing to be. There was enough of a heating history or enough of a collision history that there was some amount of melting occurring. Some of that melt went away, either to the core or to the mantle. And then there was a massive disruption, really something powerful enough to break this thing into many pieces. Then those many pieces came together again as the asteroids we know today. So they really accreted. And then a little 15 million years ago, one little chunk was thrown off when there was a collision of one of these asteroids. And that little chunk in the end made it to the ground and we picked a piece up in the living desert. This phase, a sea chondrite-like, is probably not a sea chondrite because there are no chondrules in neuralites. And so the idea could be that this body dates from before the formation of chondrules, So we're really talking about very early stages of the formation of the solar system. According to Wilson's model, that then can persist for a number of million of years to past the period that Jupiter cleaned out most of the asteroid belt. And at that time, the thing was disrupted. But now we're still talking origin of the solar system 4.5 billion years ago. So if we are looking for an asteroid field coming from this thing, then we're looking for something very old. An asteroid debris field that is 4.5 billion or so years old. One of the oldest asteroid debris fields. And we are looking for something that is rare, because of this strange discovery that all the Uralites seem to come from the same object. They have the same range of mineral properties, or Rydbergsian properties. They have the same range of oxygen isotopes in this 2008 TC3 covers the whole gamut of everything we know about Uralites. So the idea is that there's only one of these debris fields in the asteroid belt for which these meteorites keep coming. There's a continuous stream of these objects coming in. And so those are sort of the ideas behind the search. So again, we're looking for an object that was about 100 to 200 kilometers in size, formed probably before gondolas were formed in the asteroid belt. Then survived for a period of time, a couple of million years. Jupiter formed. Jupiter cleaned out most of the asteroid belt. This thing stayed there. And then around that time, there was a collision with another asteroid, and presumably it was a really big asteroid because it was a very violent collision that we're talking about when we talk about Uralites. And because of the rarity of the debris fields of the F-class, if there's only one debris field from the F-class asteroids, then this must be a rare type of event, because it's not to make this stage of planet formation, to have something be partially melted, is not that difficult to do. And to have these bodies be in a molten stage for a fairly long period of time is also not that difficult to do. So it looks like the reason we have one field is because we have had a collision between two relatively large asteroids. Yeah. And to have a collision between two relatively large asteroids is very, very rare. The biggest probability was in the early times. There were a lot. But as soon as the asteroid belt was cleared out and so on, there were very few. And so the collision probability with collisions with small asteroids is high, but so for something big to hit something else big is rare. Now, for the Uralite parent body to exist, this only had to have happened one time. So for a one-time event, probabilities are, yeah. So this is sort of what we're looking for. We're looking for an object that formed before the gondolas. This is, by the way, a picture where these are gondolas. These are round sort of circles that you see in meteorites. Many ordinary gondolites have these things. And you can see also here calcium aluminum inclusions. I don't know exactly, so usually they are a little bit irregular in shape, like these, and white in color. These things sort of mark the beginning, the very beginning of the solar system. These are the oldest little bits that we can date. And then the gondolas were formed some period after that. And then Jupiter came together some period after that. And when Jupiter was forming, it gradually moved outwards, and when it was doing so, it swept the resonances through the asteroid belt and cleaned out the whole place very quickly. And then, of course, there was this really massive disruption that was capable of destroying at least a big part of this asteroid and create a debris field. Now that brings us to today, or I should say a year ago, when Richard Kowalski discovered this little asteroid, 2008 TC3, and Alan Fitzsimmons measured this spectrum. And this is what Dr. Tahani showed, that going from 550 nanometer to 1000 nanometer, as visual, it's flat, and then that's this Pyroxene band. And this is very unusual. As Mark showed in his talk, it's very hard to find an asteroid in the asteroid belt that has exactly this spectrum. And this is how it typically looks like, of course. When Taki was measuring the very spectra, we measured also 25, and 25 is clearly different. And 25 is now identified by Mike Sawinski as being an H5 chondrite. And if we believe Amy's results, as we do, because it fits beautifully in the story, then this H5 chondrite was part of our little asteroid. It was set in there, and it got in there at the time of the big collision when everything came together again into asteroids. This thing could be the impactor, could be a piece of the impactor. Okay, so we're looking for a debris field of a uridine body, plus we're looking for some debris of an impactor. We're talking about a big asteroid, we're talking about a debris field with something that is more similar to this type of meteorites. And these meteorites have been associated with S-class asteroids. So we're looking for an F-class and an S-class debris field. Why F-class? Well, asteroids, this is now the sort of the average spectra that came out of all of Taki's measurements. This was what was observed, so this is what we now think the thing looks over the whole range. This is a T-class asteroid, typical spectrum of T-class asteroids that clearly doesn't fit. D doesn't fit, P doesn't fit, C doesn't fit. C's have a red slope, visual, and they turn over below 500. So the C's are thought to be from ordinary chondrites, so this is not a C. C's are very common. Yeah, they are linked to carbonaceous chondrite. What does resemble, the G's seem to turn over too soon, so what does resemble is the B's and the F's. And there is a bit of debate, I'll go into that, what the difference is between the two. But the point originally with defining these classes was that F meant flat. This thing was flat, had a flat spectrum in visual. All of this was based on taxonomy sort of in this area. And B meant blue sloped. So B was supposed to have a slope like this. And clearly the average spectrum here shown as a B doesn't have that slope. So people screwed up their classification scheme. That's the spectroscopic side. The other side of the story is the dynamics. To sort of get an idea, if you look in the asteroid belt, you see all these asteroids move around the sun. You need to have a handle on looking and seeing where is what. And where is what is not the spatial position of where things are in the solar system, but it is in what type of orbit are these asteroids moving. The orbit is typically described with an ellipse, and the ellipse has a single major axis, which is half the sort of length of the ellipse. It's described with an inclination, which is the tilt of the angle in which it moves. And it's associated with an eccentricity, so how elongated it is. This would be very high eccentricity, and this is a model of eccentricity. So if it's parabolic, it's 1. If it's circle, eccentricity 0. So these are the parameters we're using. We're using the size of the ellipse, we're using sort of the eccentricity, the shape of it, and we're using the inclination. Now, when an asteroid moves in space and goes around the sun, it is tugged on by the planets, by Jupiter and all the other planets. And what that does is it continuously changes these numbers, the single major axis and the eccentricity and inclination. There are these wobbles. In terms of inclination, the orbit will do something like this over time. So what people do is they take an asteroid orbit and then they calculate back in time how this orbit was wiggling. And then they calculate the average value of that. And that's called proper orbital elements. So proper just means the average value of the orbital elements over a period of time. Now if you do that, only if you do that, then you get this sort of diagrams that Mark showed. So you have single major axis, is now the length of the ellipse, and this is the inclination. That's how steep things stand on the plane. And now suddenly there's a lot of detail, a lot of structure in the asteroid belt. The first thing that pops out is that there's these empty spaces, which are called resonances, because this sort of length of the ellipse, 2.5, corresponds to a certain orbital period. The orbital period is defined as the single major axis to the power 1.5. So this, you could also have plotted the orbital period here. Now, if the orbital period of an asteroid resonates with that of Jupiter, In this case, the asteroid goes around 3 times and Jupiter goes around 1 time. Then you get into an unstable situation and your asteroid orbit rapidly changes. And how does it change? It changes by keeping the orbital period the same, sits in this resonance, but making the orbit more eccentric. And so you will end up having, if you plot this in a diagram with this eccentricity, you would go up in eccentricity. And that means that the orbit becomes, the perihelion distance shifts towards the sun, the aphelion distance goes out. The perihelion distance can come so close to the sun that it can actually come in the neighborhood of the Earth. And that's how we get a near-Earth object. So the way we get near-Earth objects is by having something end up in these resonances, and there's a lot of resonances, those are very weak resonances all over. If an object ends up in one of these resonances, then Jupiter very quickly makes the orbit eccentric. And then you end up having an object coming close to the Earth's orbit, and then it can hit. So, as Mark pointed out, we are looking for a family of asteroids, a group of asteroids, that sits close to one of those resonances, because that group is bleeding asteroids towards us. We're continuously getting some material from that group. Now, many of the families do. Like, for example, there's a group here that sits right at the edge. There's a group here, this is the Vesta family that Mike pointed out, that sits here at the group. This is the Themis family. There's a resonance here, there's the resonance here. And so on. Sorry, this could be Themis, this is no. So there is a lot of, these are all these families. These are basically debris fields of something big that sometime in the past shattered into many pieces. And they are now all found in a group there. A while back, people had discovered that if you measure the colors of those asteroids that are found in these groups, then all those colors are the same, or very similar. And so, for example, this group here, the Themis family, has all these orange colored as well. This is now a classification scheme. They're not really orange, but this is B and F type. There's B and F type asteroids here. And there is S here, this is S type asteroids here. And there's a group with the pink color, here's a group with the white color, and so on. So you have when it got hit, the pieces were spread, and you got that type of a rock out there. Basically, and I can summarize my talk right here. We're looking for something B or F, and we're looking here in the asteroid belt, where are the B's and F's families. And there's one here, which is called Polana, it's a family. There's a group here, the Themis family. There's a group called the Pallas family, which sits at 33 degrees inclination, very high. And then there are 2 smaller groups, the Theobaldus family and the Hofmeister family. So it's one of those groups. And I think we can conclude at the end of my talk that this is where asteroid 2008 TC3 came from. It's from the Polana Nisa group. We're talking about, you've seen this, no, this is just a slide to make that point again that Mark also kept emphasizing, that an asteroid spectrum does not necessarily have to be the same as a meteorite spectrum. The meteorite spectrum is a rock that has freshly broken, and the asteroid has been around in space for a very long time. It has accumulated dust, debris, so you get scattering of blue light from dust. It's been irradiated by solar wind and by micrometeoroids, which can change the mineralogy of the surface and make it more wetter in the near-infrared wavelengths. So the spectrum of the asteroid can change over time due to space weathering. That makes the search very hard, because that means that it's unlikely you're going to find a perfect match between the spectrum of the meteorite and that of the parent bodies. Now, what is an F-class asteroid? Anything that looks like 2008 TC3 from now on is an F-class asteroid. If anybody has another scheme in mind, we've decided that Eurites are F-class asteroids, so now we've identified what is an F-class The reality is that there's considerable confusion in the community on these classification, these taxonomy schemes. What is it? Where does it come from? People take these spectra of asteroids. In this case, this is usually the full wavelength range accessible from 300 nanometers to 2500. In the old days, people only looked at the visible part, so this piece of the spectrum. And Dave Tolen was one of the first to come up with a taxonomy scheme, and he came up with the B type and the F type. But originally, his F types were flat, and his B types were blue sloped. Later, people started putting in other criteria, such as albedo, giving the B's the higher albedo than the F's and so on. And none of that is really related to, also whether it's red or not, it's not really related originally to what was called an F or what was called a B. Then people started looking in the near infrared and coming up with yet again new taxonomy schemes, because clearly it was insufficient. First, Buzz and Francesca De Meo came up with a scheme. Francesca extended it to the near infrared, where they came up with a new terminology of taxonomies, and theirs is a little different than Dave's is. And they use some of the same letters. For example, they used the B for things with a blue slope, just like Dave does, but the objects classified in this scheme or this scheme can be different. 2008 3C3 is this one here, it's flat, and then there's this weak pyroxene band, and that sort of continues to be flat. Here's another weak pyroxene feature. So this is the meteorite spectrum. This is the asteroid spectrum. So clearly the asteroid spectrum was very much the same as our meteorites. The asteroid was short enough in space to not have accumulated a lot of dust, and there was no significant space weathering that would change the spectrum in this wavelength range, which is very interesting. Now the other object that was mentioned early on was 1998 KU2, and we picked that object because it is an F-class. And we were looking for F-class things with a perihelion at the Earth. And Francesco had a spectrum of it, and this is the spectrum of 1988 KU2. You can see that it's basically identical to 2008 TC3. So it's flat, and then it has a white pyroxene band. This is, as far as we know, 2008 TC3. So in this case, there's also some olivine signature. F-class. F-class asteroids are now plotted here as black dots. The B's are open circles, and plotted some C's as well. But the point is to make a distinction between B and F. What's plotted here is the blue versus visual color of an asteroid, and the ultraviolet minus blue color of an asteroid. So this is basically how ultraviolet is the asteroid, how blue is the asteroid in the visual. And the F-class asteroids tend to be sort of neutral color, flat in visual, and have a relatively dark ultraviolet part. While the blue ones are blue sloped, and they have a much steeper ultraviolet part, but they are also a little bit blue sloped in visual, so a little bit coming out a little bit higher here. So even in these colors, you can make the distinction between these two classes, and it's not always used. You can see some classes scattered up here, and some classes, so the taxonomy is not always used in the correct way, I would say. Now, if you do the same thing with the Buzz De Meo taxonomy, then you see the B's and the F's. Many of the B's in their scheme actually fall in the F class domain and the CB's also scatter in the F class, some of them. While these scatter more in the B class. In principle, you can use these colors, which many of the asteroids are at least known these colors. You can use these colors to reclassify these asteroids into that scheme if you would want to. Okay, so that said, I basically did that. I looked at all the asteroids that were either B or F. I defaulted that. And I looked at which ones were F's, which ones were B's, and plotted again this is the single major axis, this is inclination, and here this is single major axis, and this is eccentricity. So I plotted where are all those asteroids located. And so these are now all the different F-class asteroids. And you can see, like in the graph before, this is the Polana family. There's a lot of F-class asteroids found in this area. The Themis family tends to classify as B. So they're more blue-sloped. The Pallas family, which sits all the way up here, tends to classify both B and F. They're right on the border. And then there is a small grouping, the Hofmeister family that I found, the Theobald family. There are many other F-class asteroids scattered throughout the asteroid belt. Each of these could signify that there is another family there that could give us 2008 DC3. So I looked at those and to see if I could find some. And in the end, I found only one Theobald, but there was only one object known as such. Okay, so these are some of these stray F-class asteroids. So they're all flat. And Mike was saying that he couldn't find pyroxene signatures, but there are plenty of pyroxene signatures. It's just very weak, as you can see. There's always depression here. So there is a lot of those, and so all of those could be, in theory, any of those could be the origin of our asteroid. But if a single asteroid, F-class asteroid, an isolated F-class asteroid, is the source of our Eurolines, then I don't understand how that can be, because probability of collisions and so on are much bigger if you have an asteroid field, but the surface of the asteroid is hugely more than it is for a single F-class asteroid. So it's much more likely our bodies come from a debris field than it comes from a single object. And remember, we are looking for the debris field. Many of these F-class asteroids could originally come from some protoplanet that then disrupted and now scattered throughout the asteroid belt. But many of these are really big. And so it's much more likely that these are protoplanets as well. Now, Rachel Bitzel came up with a number of near-infrared spectra for some of these asteroids that are F-class in the optical. And these are some of the spectra. This is Polana. Polana is in the Polana family. It's the biggest object in the Polana family. And you can see that there is quite some variation. Many have a bit of a red slope. This is 2 Pallas, which is the Pallas family. It has more of a blue slope going down. There is a hint of pyroxene absorption, but there's clearly that absorption is very broad in many of these objects. And none of these spectra are a perfect fit to 2008 TC3. So from the spectroscopy alone, you cannot tell. You cannot say that any of these would be a good match. Although some of the basic characteristics. So this is just to show you how the Theobald family shows up. This is CMH axis inclination. Here's Theobald, and this is the little family that's associated with it. These families are known. People have looked at this data, a list of things. This is the Pallas family spectrum. Pallas itself is shown here, and these are all the asteroids known with spectra that are Pallas family. So there's also weak pyroxene there, it looks like, and then there's a blue slope. And all these objects sit at a very high inclination of 33 degrees. So it's very unlikely, you cannot create 2008 TC3 with starting out with something that's at 33 degrees inclination. You cannot change the inclination by having close encounters with the Earth that dramatically. So our asteroid does not come from the Pallas family. Hofmeister family are some spectra known as well. Most of them also look fairly flat, but all of these are small. Hofmeister itself is also small. They're also 26 kilometers in size, as you can see, because the spectra are very noisy. And that too doesn't look a very good source, because the Hofmeister family too is very concentrated. It's a very compact family. So it does. This is the resonance. Here's where the Hofmeister itself said these are all the asteroids of the family. So it does bleed asteroids in the resonance. But the grouping itself is very young. That means that this debris field was created not so long ago. And remember, we are looking for a parent body that goes back, of a collision that goes back to the formation of the solar system. That brings us then to the Polana family. The Polana family is really weird in many respects. because the planet family doesn't come alone. It comes together with an S-class debris field that overlays the planet family. And if you look at the individual F-class spectra in the planet family, you find quite a range. You find some that look more like this. And that one is actually very similar to an asteroid called NISA, or NISA. NISA is an E-type asteroid. It's the Stein's equivalent. People think it's an oblite. And it's very different because it has a huge albedo. This thing has an albedo of 0.55. All these others don't. They're all dark. But they have a very similar shape spectrum. And they're all found in that grouping. So NISA is a really interesting thing sitting there. And then Polana itself.